Good afternoon, my name is Fernando Avila and I am an assistant professor at the Polytechnic University of Valencia in Spain. Today, I am pleased to present a study developed in collaboration with my colleagues at the Sustainable Engineering Structures Laboratory of the University of Granada. The title of the study is Effect of Clay Content on the Fracture Performance of Unstabilized Rammed Earth. I will begin with a brief introduction to the motivation behind this research and its main objectives. Then I will describe the materials and methodology used in the study, and after that I will present and discuss the main results. Finally, I will conclude with the key findings. Rammed earth is a construction technique that consists of compacting successive layers of soils within temporary formwork. It is a traditional building technique that has been used for centuries all over the world, and still it can be found in numerous heritage structures. Additionally, rammed earth has today a significant potential for application in modern sustainable construction. However, and despite its growing interest, rammed earth remains a material with very limited standardization, which hinders its wider adoption in modern construction. Furthermore, most existing studies focus primarily on the compressive strength of the material, whereas fracture behavior is known to play a crucial role in the failure mechanisms of this type of structure, particularly when it is submitted to very high loads like seismic loads. Against this background, the aim of the present study is to evaluate the fracture behavior of rammed earth and, more specifically, to investigate how clay content influences its behavior. In unstabilized rammed earth, where no cement, lime or other stabilizers are added, clay acts as the only binder in the mixture. Therefore, it is reasonable to expect that clay plays a significant role on the fracture performance of the material. Our objective was also to determine whether fracture behavior can be predicted as a function of clay content, and also to complement this evaluation using non-destructive testing techniques. To achieve this goal, 5 soil mixtures with increasing clay content were selected, ranging from 25% clay in soil A to 100% clay in soil D. Typical clay contents for rammed earth construction generally range between 25 and 40%. Therefore, soils A and B represent realistic construction materials, soil C has an extra of clay, and soil D, consisting entirely of clay, is not practical for rammed earth, but it was included here just as a reference material for comparison purposes. Using these soils, prismatic specimens were manufactured, with 5 specimens produced for each series. The specimens were manufactured mixing the soil with its optimum moisture content, obtained through proctor tests, and compacting the mixture of soil plus water into 3 layers. The specimens measured 10 per 10 per 45 centimeters and were tested under 3-point bending tests, which is a standard method for evaluating the fracture behavior and fracture energy in quasi-brittle materials. The support span was set to 40 centimeters and a vertical load was applied at the top. In the absence of specific standards for rammed earth, the concrete standard EN 14651 was adopted together with recommendations available in literature. As shown in the image, all specimens were notched at mid-spine with a notch depth equal to 1/3 of the specimen height. Here you can see a photograph of one of the specimens immediately before testing. Regarding the non-destructive testing program, two techniques were employed. First, three free resonant column tests were performed. This method allows the determination of the dynamic elastic properties of the material by mechanically exciting a specimen of known geometry. The test was performed in longitudinal, transverse, and torsional vibration modes, and you can see on your left. Second, ultrasonic pulse velocity tests were carried out in which the propagation speed of acoustic waves through the specimen can be measured. This velocity of the waves depends primarily on the material's density and stiffness. Ultrasonic pulse velocity tests were carried out in this case in longitudinal and transverse directions. Let us now move on to the results, beginning with the 3-point bending test. The figure shows the load displacement curves, also called P-delta curves, obtained for all series. In each case, we observed an initial approximately linear hardening branch up to the peak load, followed by a softening branch. As clay content increases, both the maximum load and the displacement at peak load increase. The maximum load rises from 536 Newton to 820 Newton, increasing at 53%. It should be noted that for Series D, composed of pure clay, the post-peak response could not be recorded during the test because the specimens failed in a brittle manner immediately after reaching the peak load. The most important parameter obtained from these tests, however, is the fracture energy, GF. This parameter is defined as the ratio between the work of fracture and the ligament area. The ligament area corresponds to the cross-sectional area of the specimen above the notch, while the work of fracture is calculated as the area under the P-delta curve. Because experimental measurements do not capture the entire tail of the curve, an additional correction must be applied to account for the unrecorded portion. The methodology proposed by Elias in 1992 was adopted for this purpose. As shown in the graph in red, fracture energy increases significantly from approximately 16 Newton per meter to 26 Newton per meter when clay content increases from 25 to 65%. Since the post-peak behavior of Series D could not be measured, a partial fracture energy calculated from the beginning of the test up to the peak load was also defined for comparison. In this case, a marked increase can be observed also, in green in the graph, for specimens with high clay contents, particularly Series C and D. The next objective of the study was to develop a model capable of predicting fracture energy. Based on the experimental P-delta curves, you can see this figure again in the slide, a piecewise analytical function was proposed. This function consists of a linear segment representing the initial hardening branch up to the peak load, followed by an exponential function describing the softening branch. The model depends on three fitting parameters: K representing the slope of the linear branch, delta P defined as the displacement at peak load, and alpha, which defines the shape of the exponential branch. These three fitting parameters were subsequently expressed as linear functions of clay content through a regression analysis that minimized the combined fitting error across all four series A, B, C, and D. The resulting expressions are shown on the slide. Using these relationships, the fitting parameters were calculated for the clay contents of the series, meaning 25, 40, 65 and 100%. And then the corresponding analytical p-delta curves were generated. The results of this fitting procedure presented here. For each series, the experimental data are shown with dashed lines, while the analytical predictions are represented by continuous lines. As can be seen, the proposed formulation reproduces the experimental behavior very accurately, with correlation coefficients exceeding 0.95 in all cases. The analytical model can also be used to calculate peak load and fracture energy directly. The comparison shown here indicates very small differences between analytical and experimental results. Peak load differences range from 3 to maximum of 15%, while fracture energy differences remain always below 5% for all series. The model allowed to estimate the total fracture energy of series D, which could not be calculated experimentally due to the brittle failure of the specimens after peak load. A value of 34 Newton per meter was obtained. This is the maximum of all four series. Furthermore, the model can be used to predict the entire p-delta curve and the corresponding fracture energy for any clay content from 0 to 100%. And as shown on the left, the initial slope varies only slightly between clay contents, whereas significant changes are observed in both the peak load and the softening branch. By integrating these curves, the fracture energy can be obtained directly as a function of the clay content. This is illustrated in the graph that you can see on your right. The final stage of the study was focused on correlating the results of the non-destructive tests with the fracture energy, which was selected as previously stated as the main indicator of fracture performance. The results on this slide correspond to the free resonant column tests, and you can see that a reasonably strong correlation is observed for the longitudinal vibration mode with a coefficient of determination of approximately 0.75, whereas moderate or no correlation is found for the transverse and the torsional modes. Similar analyses were carried out using the ultrasonic pulse velocity measurements. In this case, the longitudinal measurement showed only a modest correlation with fracture energy, while no meaningful correlation was observed for the transverse measurements. However, when a multivariable linear regression was performed using the longitudinal results from both non-destructive testing methods, the predictive accuracy improved considerably, achieving a coefficient of determination of approximately 0.80. To conclude, The results of this study demonstrate that clay content has a clear influence on the fracture behavior of unstabilized rammed earth. Increasing clay content leads to higher peak loads, greater ductility, and increased fracture energy. In addition, a piecewise analytical formulation was successfully developed and shown to accurately predict both the Peedelter curves and the fracture energy. The results also indicate that combining non-destructive testing techniques provides a reliable means of estimating the fracture energy of rammed earth. Overall, the findings of this study provide an effective predictive framework for assessing the fracture performance of unstabilized rammed earth and may serve as a basis for future material optimization and design approaches. Thank you very much for your attention. I would like to acknowledge my colleagues at the University of Granada for their collaboration in this work, as well as the Congress for inviting me. I will be now happy to answer any questions and discuss any aspects of the study. Thank you very much.